In this video, we're going to explore r squared, that is the coefficient of determination. We'll look to answer two questions. What is r squared, and how is it calculated? And I suggest copying these notes down, and we will show an example about midway through the video that might clarify it. If you don't fully understand the notes up front, that's okay. The example should clear it up. Definition. R squared is the coefficient of determination. That's the fraction or percent of variation in, by variation we mean change, variation in y explained by variation in x. The coefficient of determination is a percent that tells you how efficient your model is at predicting some y given some x. Okay. The coefficient of determination, again, we signify it with r squared. And this is literally the square of correlation, which we saw earlier in the chapter was r. So one way to find r squared is to simply square the correlation. It is defined as SST minus SSE divided by SST. So you can see it's going to be some sort of proportion here, and we can convert that proportion to a percentage. Well, what are these SSTs and SSEs? SST is the sum of squares about the mean y. It is the sum of each y value subtracted from the mean y quantity squared. What is SSE? Well, SSE is the sum of squares for error. That's also called the residual squared. SSE is calculated by summing up each y minus y hat, that's the predicted y, and squaring. This quantity here you perhaps have learned already. This is the residual. Y hat is the predicted y. It's the y value that's predicted by our least squared regression line. Okay, so we are going to use this SST and SSE quantity to see if we can find a couple of r squareds. Alright, first example. Let's say we have a situation that is perfectly linear. Here I've plotted the points. 1 goes to 4, 3 goes to 5, and 5 goes to 6. You see them over here in red. Well, since these are perfectly linear, the regression line, the y hat, falls directly over the top of those. Hopefully you know by now that r in this case will be 1, therefore r squared is 1. That is, the change in y is perfectly predicted by the change in x. We'll see this on the calculator. Stat edit. I'm entering in 1, 3, and 5 in list 1, 4, 5, and 6 in list 2. Alright, now to the home screen, I'm performing a linear regression, list 1, list 2, and pasting that over y1. Hit enter. I see I have a y-intercept of 3.5, a slope of 0.5, r squared is 1, and r is 1. Let's take a picture, let's take a look at the points graphed and then the regression line. Zoom 9. There you see the points, there you see the line falls perfectly on those points. Since it's linear, the regression line is right through those points. Well, let's see if we can use this formula that we've just seen to calculate. Okay. We're going to need a couple of more quantities now. We're going to need the quantity y minus y hat quantity squared, and we're separately going to need the quantity y minus y bar quantity squared. This y bar is our mean y. This y hat is our predicted by our regression equation. Well, in this situation that's perfectly linear, clearly y hat will be the same as this, and I can come to my table and see. Coming to my table, I'm going to enter in 1, 3, and 5, and it's going to produce 4, 5, and 6. 1 produces 4, 3 produces 5, and 5 produces 6. They're perfectly aligned. So there is no error. The y minus the y hat is 0 for each one of these. Alright? So, summing these numbers obviously is 0. This number here is the sum of y minus y hat quantity squared. We didn't miss it all. The sum was 0. Now let's look at this, y minus y bar. Well, first let's calculate y bar. In this case, we have 4, 5, and 6. Adding these together, that's 15. Dividing by 3 is 5. So in this case here, our y bar is 5. Let's graph that line here. 1, 2, 3, 4. Yes, 5 here. I'm graphing this line. This line is y bar, our mean y. It's 5. What's the significance of this y bar? Well, you could think of this as being the worst possible reasonable guess. This y bar is not sensitive to changes in x at all. It's just saying, regardless of what x you give me, I'm going to guess the average y. That's a reasonable guess, to always guess the average y. So this is the worst possible guess, meaning we weren't at all concerned what the average x was. Now let's look at each one of these, subtracting from the y and squared. Well, y 4 minus y bar 5, that's negative 1. Quantity squared, that's 1. Y 5 minus y bar 5, that's 0. Quantity squared is 0. Y 6 minus y bar 5 is 1. Quantity squared is 1. That's each one of these values. Now I want to find that sum. 1, 0, 1, that's 2. So in this case, this is the sum of the squared residuals. The sum of, the sum of the total squares about the mean. Y minus y bar quantity squared. That's 2. Okay. Now with these two values, we are ready to find r squared. Again, r squared is equal to SST minus SSE over SST. Well, the SST, the sum of the total squares, is this number 2. SST is 2. SSE, that's this number here, 0. SST down here, 2. So what we have is 2 minus 0, that's 2. 2 divided by 2 is 1. Our r squared here is 1. And that 1 is 100%. 100% of the change in y is explained by the change in x, because our situation is perfectly linear. Alright, let's look at the next one. Okay, now we have 3 pairs with 5, 4 pairs with 9, 5 pairs with 7. Here I plotted those points. 3 to 5, 4 to 9, 5 to 7. You can see that these points aren't so well correlated. They're still correlated and they're still positive, but clearly they're not linear. Here is the graphed regression line, the y-hat. This time we have some residuals, a difference between the actual y and the predicted y. Alright, going back to my calculator, and let's take a look at that. Stat edit. In list 1, 3, 4, 5. In list 2, 5, 9, 7. Performing the regression. Here you can see that R is 0.5. It is still a positive correlation, and 0.5 quantity squared is 0.25. We see the line has a y-intercept of 3 and a slope of 1. Looking at the graph, I should hit zoom 9. You can see it bears some resemblance to my picture over here. The scale is different. That's why ours looks a little steeper than what the calculator has drawn. Let us go back and calculate the two quantities again. Okay. This is y minus y hat quantity squared. Alright. That is our SSE. SSE. Next, y minus y bar quantity squared. This is the SST. This is the total sum of the squares about the mean. This is the sum of the squares, the square errors, the residual. Alright, let's calculate these. Okay, I want to go and look at where the regression line is predicting our points to be. I'm looking at my table. I want to know what is 3 predicted to be. 3 is predicted to go to 6. It actually goes to 5. So 5 minus 6 is -1. Quantity squared is 1. Alright, what is 4 predicted to go to? The line predicts 4 will pair with 7. So 9 is my y, 7 is my predicted y. 9 minus 7 is 2. Quantity squared is 4. Alright. What is 5 predicted to go to? We have it here. 5 is predicted to go to 8. So 7 minus 8 is -1. Quantity squared is 1. The sum of these, my SSE, adding these up is 6. SSE is 6. Alright. Sum of the total squares. I need to find the mean y. Well, adding up my y's, 5 and 9 is 14, plus 7 is 21. 21 divided by 3 is 7. So, in this case, y bar is 7. Let me draw that line in. 1, 2, 3, 4, 5, 6, 7, right here. This is essentially the worst possible reasonable guess. This is the line. Y is 7. We say y bar is 7. It's our mean y. If we aren't sensitive to the x, this would be the worst reasonable guess. Okay. If we weren't sensitive to the x, it's the best reasonable guess. Right? It takes no account to what the x is. So the first y is 5. Y bar is 7. 5 minus 7 is a -2. -2 quantity squared, 4. Next one, 9. 9 minus 7, 2. 2 squared, 4. Next one, 7. 7 minus 7, 0. 0 squared, 0. Summing, this is 8. My SST is 8. Okay. Now I will find R squared. R squared is SST minus SSE divided by SST. In our case, SST 8. SSE 6. SST 8. 8 minus 6 is 2. 2 over 8. 2 over 8 is 1/4. And 1/4 is 0.25. In this case, R squared is 0.25. that is 25%. 25% of the change in y can be explained by a change in x, to be 0.25. Let's go back to the calculator and verify that that's what it is. Stat edit 3, 4, 5, 5, enter, 9, enter, 7, enter. Man, let's hope this is right. We sure have invested a lot of time in it. Second quit, second enter. Bingo. R squared is 0.25. That's what we just calculated. All right. Lastly, we're looking at 354255. 354255. You get this V-shaped arrangement. As you might imagine, the correlation here is 0. We should not even perform a linear regression here because clearly this is not a linear situation, but for the purposes of this exercise we will. Stat edit 3, 4, and 5 are my x's. 5, 2, and 5 are my y's. Clear, second enter, bring back the statement. Here we see both r squared and r are 0. Looking at the graph, there you see the points, and there you see is our regression equation. What is that regression equation? It's 4 plus 0x. The slope is clearly 0. It's a flat line, and the y-intercept is 4. All right. So here you see this is my regression line. 1, 2, 3, 4. That is the regression line. Okay, so back to our calculations. First, we're going to calculate the sum of the square errors. That is y minus y hat. How far each one of our points is from the predicted. All right, here we go. Well, we know what it's going to predict. It's going to predict 4 the whole way. 3 goes to 4, 4 goes to 4, 5 goes to 4. Our line was horizontal there. So, we're predicted 5. Our actual y is 5. Our predicted is 4. 5 minus 4 is 1. 1 quantity squared is 1. Our actual y is 2. Our predicted is 4. 2 minus 4, 2. Quantity squared, 4. 2 minus 4 is negative 2. Quantity squared is still 4. Now 5. 5 minus 4 is 1. 1 quantity squared, 1. So, adding up these values, 4, 5, 6. The sum of our residuals squared is 6. Now we will examine the SST, that is each y minus the mean y, quantity squared. Well, what is the mean y? Looking at my y's here. 5, 10, 12. 12 divided by 4, 12 divided by 3 is 4. Our y bar here is 4. Aha! Here you see our situation. When I graph this one, it's going to be indeed right over the top. So we see that y bar and y hat are equal to each other. The predicted and the mean are right on top of each other. Our predicted is no better than the mean. Since these are right on top of each other, clearly this will be 1, 4, and 1. So the sum here is 6. Our predicted y, the y hat, is exactly the same as the mean y. So I hope you know where this is headed. We're going to get an r squared of 0. Again, r squared is SST minus SSE divided by SST. So in our case, 6 and 6. 6 minus 6 divided by 6. Well, 6 minus 6 is clearly 0. 0 divided by 6 is 0. In this case, r squared is 0. That is 0%. None of the change in y is explained by a change in x. If we look at the top and bottom, I think it provides the best illumination, okay, of what r squared is. In this case, there was no error in the prediction. Since there was no error in the prediction, our model was 100% effective. The points fell right on the predicted line. As opposed to our bottom one, our residual error was exactly the same as the total error. There was no value at all, no added value to our prediction. We might as well have just guessed the mean y in this case. SST and SSE were the same. Since they were the same, we had 0% there.